Okay, wonderful. We've got the recording going, and we're going to resume our discussion from last time. You will recall, last time we proved a remarkable result. We proved this result for the case of 1 degree of freedom. We had just one variable q. It's possible to go through the proof for an arbitrary number of degrees of freedom. There's really no fundamental complications, so it was very illustrative to go through that for 1 degree of freedom. We'll just leave it at that. Okay, so it's remarkable again. This is the total time derivative of the Hamiltonian minus the partial time derivative of the Lagrangian. We're really just interested in the special case and there's a special case that we like here. It's when the partial derivative of the Lagrangian with respect to t is 0. Okay, if that's true, then we have that the total time derivative, so the best way to write this is that the total time derivative, okay, and we made some remarks on this last time. You could say that the Hamiltonian is constant, but if you do that, if I just write Hamiltonian equals constant, that's a little bit misleading. It is not globally a constant across all of phase space. We'll talk about phase space later in the course. The right way to say it is the Hamiltonian is constant along an orbit. Okay, so this is important to us. And remember, we're in the midst of a very amazing story. We started with 6 degrees of freedom. This was the problem of 2 point particles interacting via a central force. And we were careful to treat the general case of an arbitrary central force. We're really most interested in the gravitational problem where the force is a gravitational interaction, but we will make remarks on some other possibilities. Okay, there are certainly other cases. So 6 degrees of freedom. We made use of the translational symmetry to arrive at an equivalent problem here, a 3 degree of freedom problem. Then we identified the constancy of the angular momentum vector, and this enabled us to study the motion in a 2-dimensional space perpendicular to the angular momentum vector. And having done this, we reduced the difficulty to a 2 degree of freedom problem. Okay, then that was a problem in a 2-dimensional space. We went to plane polar coordinates with r and phi, and then we observed that the constancy of the z component of the angular momentum enabled us to reduce this to a 1 degree of freedom problem. Okay, so this was a great triumph of classical physics. And in our last meeting, we talked about this equivalent 1 degree of freedom problem and the fact that we can solve this 1 degree of freedom problem. Okay, how do we solve it? Well, really, we use this idea here. The Hamiltonian is constant along an orbit. That is to say, the total mechanical energy is conserved for this 1 degree of freedom problem. So let's take a moment to remind ourselves what we're doing. And we'll save a little bit of time here if we look at our lecture notes. Yep, the lecture notes. Yeah, here's a big time saver because we have a lot of stuff we need to cover. So these are some lecture notes from our last meeting. And we got to this 1 degree of freedom problem. Okay, I think I should orient it. This is pretty good like this. The equation of motion here is mass, remember mu is the reduced mass, the product of the two original masses over the sum. So that's a mass parameter times, this is a one-dimensional acceleration. We are now working in a one-dimensional world. We have a single r axis. That's our one-dimensional space. And there's a particle of mass mu. And mass times acceleration is the force. The force is minus the gradient of this effective potential energy. Okay, now what we remarked earlier in today's meeting is that the total energy is conserved, right? Because the Lagrangian has no explicit time dependence, the total energy is conserved. There's another way to see this. Okay, let's talk about an equivalent way to see that the total energy is conserved. It's useful to go through the mathematics of this. So what we'll do is go like this. We'll check the document camera, and we're looking at pretty good alignment here. And now we can look at this equation. What happens if we multiply both sides by r dot? Okay, let's be very careful. I've multiplied the left side by r dot. Okay, I've multiplied both sides. Again, this was the so-called equation of motion. That's the differential equation that governs the motion. Now, if we multiply both sides by r dot, something wonderful happens. We recognize both the left-hand side and the right-hand side as a perfect time derivative. You see, the left-hand side is the time derivative Isn't that cool? If you take 1/2 mu r dot squared, if you compute the time derivative, the 2 cancels a half, and then you have mu times r dot times the derivative of r dot. So the left-hand side is this nice time derivative. The right-hand side is minus the time derivative of u effective. Okay, now that's very compact notation. Sometimes it really does help to emphasize we're talking about the effective potential, and we have a functional composition with r of t. So you see we use the chain rule. How do you compute the total time derivative of this functional composition? Well, the chain rule tells you first you must differentiate u effective. It's a function of a single variable, so the derivative is just indicated with a prime. Then you must multiply by the derivative of what's inside here, and we have special notation for dr dt. It's just r dot. Okay, wonderful. So we've shown that this total time derivative is minus this total time derivative. Okay, it stands to reason that if you bring this term over, you have an object whose total time derivative vanishes. We've just shown 1/2 mu r dot squared plus u effective Okay, so this is an alternative way. Of course, what we've just shown is fully equivalent, right? Constant along an orbit. Okay, so what we've done here, we've shown that the total mechanical energy is constant along an orbit. It's useful to go through this calculation because there's some interesting structure here as you recognize the perfect time derivatives, right? We recognize the left-hand side as a perfect time derivative, and we recognize the right-hand side as a perfect time. This occurred after we took the equation of motion and multiplied both sides by r dot. Okay, so this, as you know, from the earliest days of our summer session, at the beginning of the summer session, we had a lot of fun using this idea to compute the time it takes for the particle to travel a certain distance, because this constancy allows you to solve, okay? You can solve this for r dot, right? This constant here is the total mechanical energy. You can solve this for r dot, and this is something we studied intensively at the beginning of the session. Okay, so at this point, we can declare that we have a solution to this problem. Notice the hierarchy. When we got to this one degree of freedom problem, we were able to solve it. And when we say solve, solve in the sense of integration, we've reduced the problem to that of evaluating some integrals. And evaluating integrals is considered much simpler than solving differential equations. So at this point, we declare that we've solved the differential equations. That's a difficult task. And we have only now to evaluate some integrals. So there are a variety of technical issues here as we evaluate the integrals. But since at this point we can declare that we've solved the problem, it is appropriate that we take a moment to reward ourselves. Let's reward ourselves for all this hard work and look at some fascinating things that NASA has done over the years. And we'll talk about how these amazing missions, NASA missions, how they relate to these topics in Chapter 8. So what I'm going to do is click on the share. I'm going to click here. Okay. Now, well, what we're going to do is actually click here and click here and click here. Okay. Yeah. So you see these are some slides from the spring of 2014. Back when I taught this course in the spring of 2014. The reason I mention that is as we go through the slides, you may see a reference to how far certain spacecraft are from Earth. Well, now they're even further. They just keep on going. Okay, so we're going to talk about these wonderful things that we have learned in Chapter 8 and talk about interplanetary journeys, gravity assist trajectories. This is very important. It's a technique that is widely used. And then error analysis, okay? It's necessary to do an error analysis. We have to understand how accurate these trajectories are. Okay, so okay, let's see. It's scrolling in a funny manner here. Okay, so we're going to talk about Voyager 2, launched way back in 1977 and still operating today, 103 astronomical units. Okay, that number was correct back in 2014. Now it's even further. Okay, one of the most distant human-made objects. It's hard to find human-made objects out there, way out there where these spacecraft are. Okay, you can get the status of the mission here from the NASA. Unfortunately, that thing came down, and I think if I just wait it out, it will go away. There, it went away. I was trying to point at the URL. No, it came back. I'm trying to point at the URL, and I'm just going to have to wait it out again and just verbally state at the top of the page, you see nasa.gov, nasa.gov. That's where you can get the mission status. Okay. Way back in 1977, we would print things on paper. I know it's hard to believe, but if you want the mission status, this document that we're looking at here, mission status bulletin, you would send them a little bit of money for postage stamps, basically. And here you have this status from November 29th, 1977. Now, what's really important to us is this diagram, because there are several things that we're going to discuss about these orbits. We're going to talk about elliptical orbits, hyperbolic orbits, etc. Now, I'm pointing with the mouse pointer. Here we have the Earth. The Earth is orbiting the sun, and let's say that's an elliptical orbit. It's not a perfect ellipse, but it's pretty close. And what's important to it now is that the date, you see October 12th, October 22nd, November 1st. These triangular markers indicate the position of the Earth along the orbit. So as we go through some of the details now of these orbits, it's very important to have this distinction. We're going to write down a fairly simple formula for an elliptical orbit. And when we say that, we're referring to the shape of the orbit. So this formula would let you plot this solid, you see the solid curve here, that's the Earth's orbit around the sun. Same is true for Mars. We have a solid curve, and you could plot that solid curve. It's quite easy to plot the solid curve. What's much more difficult is the time parameterization. So getting these markers on here, right? And that's important to us because really our goal in mechanics is to solve for the motion. And typically we understand that to mean write down a formula that tells me where the particle is as a function of time. Okay, for this problem, for these orbits, that's extraordinarily difficult to do. We'll have some transcendental equations. They're not covered in Taylor's book, but I feel we should say a few words about these equations. And these equations enable you to put these markers along the orbit, so now you know where the particle is. In this case, the particle is Mars. I'm pointing to the Martian orbit. Now, the other two here, you see we've got Voyager 1 and Voyager 2. And so this mission status report is telling you the location of those spacecraft. So this diagram here, it's a nice illustration of two of the fundamental concepts here. The notion of the shape of the orbit, and again, right there in the Chapter 8 summary, you have a formula. One of the centerpieces of Chapter 8 is the formula for the shape of the orbit, and that empowers you to draw these solid lines. What's not in the Chapter 8 summary, and of course it will not be on the exams, is the idea that you can actually put markers here for now bringing in information about time. Okay, when you draw the solid curve, you don't know exactly the time when we reach each of these points. Okay, so this is a nice illustration from the Voyager mission. Now, gravity assist maneuvers. How do you get your spacecraft to travel so far from home? Okay, this is a nice diagram. Again, notice the URL, it's nasa.gov. The horizontal axis here is the distance from the sun, again, measured in AU. You see the Earth is at 1 AU. That's the definition of an AU, the average distance between the Earth and the sun. Okay, what's going vertical here? It's a little bit unfortunate. It says heliocentric velocity. It should say heliocentric speed. The speed is the length of the velocity vector. Okay, but sometimes people slip up and they accidentally use the word velocity. We can typically get through these situations because you see there's just a single number here. There's no vector. Really, the velocity is a vector. Okay, that's in kilometers per second. So you see what happened here. The spacecraft is approaching Jupiter, 5 AU from the sun. And as we pass by Jupiter, you see the speed shoots way up here to nearly 30 kilometers a second. And as we leave the Jovian system, it slows back down. But you see, we've profited from that maneuver, okay? The crucial thing when you design these orbits, these trajectories, is to plan out, and we'll be doing this on the homework, plan out the so-called swing by. Sometimes these maneuvers are called swing bys, and sometimes they're called flyby. Flyby is rather unfortunate because it's not flying, it's falling the whole time. But that's just the term that is used. We're gonna fly by Jupiter, we're gonna fly by Saturn. Notice Neptune was a little counterproductive. They did that on purpose. This was not an accident. It's just the way we passed by Neptune there. It actually slowed down the spacecraft. Who cares? We have plenty of kinetic energy at that point. So this is, again, it's a nice diagram showing you exciting applications to NASA missions, nasa.gov, and using the framework that we've set up in this chapter. Okay, let's go on to the next. Now here I say view from the North Pole direction. I know that's a funny choice of words, but the important thing is when you look at the solar system, okay, you have all of these objects revolving around the sun. We're talking about the major objects like the planets. And as you know, the sun rose in the east this morning. There's a sense of rotation. Okay, so the sun rising in the east, that's because the Earth is spinning on its axis, and we've drawn the diagrams with the right-hand rule, etc. If you view from, when I say North Pole direction, I'm talking about the North Pole of the Earth. Just keep going out in that direction, several AU, quite a few AU, and then look back down on the solar system. This is what you see, and everything is going counterclockwise. Okay, that's the usual right-hand rule. Okay, so again, this is a diagram showing you the launch, and then we have the various swing-by maneuvers. Okay. Now, this is an important document here. Let's talk about the author Troy Goodson, Donald Gray, Jung-Sun Han, and Fernando Peralta. Okay, document. This was back in 1998, Jet Propulsion Laboratory, Caltech. Again, wonderful. You know, I went to a conference there some years ago. Wonderful place, lots of fascinating stuff going on. And we're going to analyze, this is a different mission now, this is Cassini. How do you analyze the accuracy of the trajectory, and how do you make corrections? All right, this is crucial. So this is an interplanetary trajectory. We have the orbit of Venus. This particular spacecraft, we had a Venus swing by June 24th, and there was another Venus swing by. You see, April 26th of 1998, there was the first Venus swing by. All of this was carefully planned out. So April 26th of 1998, we swing by Venus, we pick up some kinetic energy. This is profitable for the spacecraft. Then we come back June 24th of the following year, 1999. We swing by again. It just keeps getting better with these carefully planned maneuvers. Okay, what we want to talk about here, and we will see this stuff in chapter 8. Again, here we have the horizontal axis on this diagram is the time, and vertically, the specific energy. That's correct, right? The specific energy means the energy divided by the mass. So the units are kilometers squared per second squared. We're negative here because for bound orbits, it's a negative number. Okay, so there's the launch. DSM, that's a deep space maneuver. Those are expensive. A deep space maneuver means you actually switch on a rocket engine, you burn some fuel, and you see in the table at 451, this is measured, the language they speak is delta V. When you switch on a rocket engine for a certain amount of time, that's in integration time, acceleration, you get a delta V. The upshot is you have a certain delta V budget. So that was a rather expensive deep space maneuver there, and that occurred here. Okay, then you have the various swing bys. Let's not talk about this bias removal, that gets a little technical. Then the Saturn orbit, right? The Cassini spacecraft was put into orbit around Saturn, and then a probe was landed down on a moon. Okay, so amazing stuff. But again, you have the swing by here, the second Venus swing by. Notice the first Venus swing by. Wonderful, look how much energy we got by swinging by Venus. Then we swing by Venus again. Then we swing by the Earth. And notice here in this document, 10 to the minus 6. The 13 there, that's a footnote, but 10 to the minus 6th. It was considered to have, it's acceptable to have a probability of 1 in a million to strike the Earth. Okay, that was the way this mission was planned. If for some reason it did strike the Earth, of course, it's very unlikely it would hit somebody and hurt them. Probably it would land in the ocean. Okay, but it's interesting to see those numbers here. They chose this number 10 to the minus 6. We're going to see more examples of those kinds of numbers. Okay, now here's the error analysis that I mentioned. The shaded region is the disk. Okay, imagine looking at a picture of the planet Venus and zooming in, so you're looking at essentially the surface of the Venus. So to the left of this line, that shaded region, that's Venus. And here we have some markers, the altitude. So Venus plus 100 kilometers. Okay, as you know, the atmosphere of Venus is very dense. So here, this line is 100 kilometers above the surface. This is 200 kilometers. That was considered the minimum safe altitude, right? And you can make comparisons with satellites orbiting the Earth. You're talking hundreds of kilometers above the surface of the Earth. Okay, so again, the atmosphere is very dense. And here's a funny fact about how dense the atmosphere of Venus is. Let's talk about a different mission for the moment. There are missions where you land a spacecraft on the surface of Venus. And those are remarkable because initially they deploy a parachute as they're approaching and preparing to land. And at a very, very high altitude, they actually cut the lines to the parachute. Just snip, snip, parachute's gone. The rest of the descent is free fall, but the atmosphere is so dense that the result is a soft landing on the planet. Okay, you wouldn't want to do that here on Earth. You would just make a crater. But that's a perfectly good way to go for landing on Venus. This mission here, the Cassini mission, didn't land. And the purpose was to swing by Venus. And here you have predicted TCM2 delivery. So this is a trajectory correction maneuver, right? You have the spacecraft traveling through the solar system. The plan is to go swinging by Venus here, a mere 300 kilometers above the surface. If you can do this correctly, you will profit immensely in terms of accelerating the spacecraft onwards on its journey. But it's necessary to do an error analysis. And this elliptical region is an error analysis. So with TCM2 here, that's trajectory correction maneuver 2. Without trajectory correction maneuver 2, you would have impacted here onto Venus. So earlier, they did trajectory correction maneuver number 2, and that changed the trajectory to here. Okay, so that, again, this is kind of an example of the error analysis. Now, what we can do with our formulas in chapter 8, we can figure out for different locations. So ideally, we would want the spacecraft to pass through somewhere inside this ellipse. And this ellipse is not an elliptical orbit. It's a region in the diagram that has an acceptable, these are considered acceptable places for the spacecraft to pass through. Okay, so these are the kind of things they do when they analyze and plan out the orbits. If there was an error here, then later you would correct for it again. Okay, so our point right now is to appreciate that the formulas we will use here in chapter 8 and looking ahead to a future homework assignment. So after the midterm, the next homework assignment will be due Tuesday following the midterm. We're going to start looking at these kinds of orbital calculations and see how they relate to the nice formulas we're deriving here. Okay, I'm going to click stop share. Wonderful. This takes us back to our lecture chalkboard, so to speak. So that was a nice motivational pitch that this is fascinating stuff with interesting applications. And again, to understand this hierarchy, this is the real key. We've solved the 1 degree of freedom problem. We have a particle moving back and forth. If it's an elliptical orbit, then for the 1 degree of freedom problem, you have a particle moving back and forth along this R axis. That's a one-dimensional space. But we have to understand how to reconstruct the motion, go back to the 2 degree of freedom problem. And there are results, some results in chapter 8 in the summary. In particular, again, the centerpiece, this formula for the elliptical orbits, the hyperbolic orbits, and the parabolic, I should say hyperbolic trajectories, parabolic trajectories, etc. Okay, so let us now start delving into the details. We want to delve into the details of this picture and how you reconstruct the motion. Okay. So at this point, we're very happy with the 1 degree of freedom problem. We know how to solve this. You remember at the beginning of our summer session, we used the constancy of the energy to write down an integral, right? We solved this for r dot. No problem there, it's just a square root, right? You just solve it for r dot. We're going to talk about the difficulty of some of these integrals. Okay. And the upshot is we can now work our way towards first the solution of the 1 degree of freedom problem. Then we want to solve the 2 degree of freedom problem. Okay, so let's remind ourselves, how do you do this for the 1 degree of freedom problem? Again, this is the kind of stuff you could see on the midterm, right? We've been studying this since day 1 of the course. Okay, so you solve for r dot as a function of r. Remember, this is the crucial thing about classical mechanics, understanding and keeping in mind what is a function of what. And here, this equation for the constancy of the energy along an orbit, you can solve it and find the speed, right, as a function of position. Notice we have not found the speed as a function of time. If we did have the speed as a function of time, you would just integrate that and get the position of the particle. But we have the speed as a function of position. So what do? Well, we have to integrate as follows. Last time we talked about the turning points, right? There are two classical turning points. So R min to R okay. And what is this? This is T. Okay, so this is a big milestone, and we've been harping on this since day one of the course, right? Now we have T as a function of R, right? Let's really emphasize that. What I will do is write the text and then draw some arrows. We have T as a function of R. And why am I justified in saying that? Well, let's redraw it like this. Okay, I think we're going to scoot this like so. T, this equation gives you T, there's the T, as a function of R. Where's the R? Here's R. That's important to understand. We have T as a function of R, right? And you would write that in terms of our mathematics notation. We would say this is T as a function of R. This is how we indicate functional dependence. The dependent variable is T, the independent variable is R. Later today, we'll talk about how you would solve this to get R of T. That's what we really like to do in mechanics, is solve for the position as a function of time. But that's considered elementary in terms of the difficulty level compared to solving these differential equations. So typically people declare victory when they have T as a function of R. Okay, let's follow the flow of information. If T is a function of R, then R is the independent variable. A user of this function would specify a value of R. The value of R goes here. It's the upper limit for the integral. Inside the integral, you have a different variable. It's R prime. The prime is certainly not a derivative. It's, again, just a means of producing a symbol that is different from R, but has a similar appearance. Okay, so the variable of integration is the R prime, and we're plugging in R prime here. Okay, so this integrand, it's good old distance equals rate times time, and the entire thing inside the integral here is just dt. It's the differential time, right? dr prime divided by r dot. Yeah, so this again harkens back to the early days of the course, and let's appreciate at this point we have a formula for t as a function of r. Okay, what can we do for the 2 degree of freedom problem? Well, there's some good news here. Because we've already solved all the difficult things, we can now use the constancy of the angular momentum. We have d phi dt equaling, remember this cursive lowercase l, that's the angular momentum, over mu r squared. Okay. So again, the flow of logic is that you could invert this. All right. In principle, you could invert it. Certainly, if you have a computer, you can invert it. In practice, it's a difficult algebra problem, but you could invert to get R of t. Okay. So at this point, we've essentially found the function R of t. Again, it's just a functional inversion. That's considered easier than these other operations. So you have R of t. Well, if you have R of t, then look at this next equation. This is what we proved for the conservation of angular momentum. Now this R is considered a known function of time. You simply integrate to get your delta phi. Okay, so the upshot here is you have phi as a function of time, right? It equals phi at time 0 plus an integral from 0 to t. That constant, the variable integration must have a different name, so dt prime, and it's mu r squared of t prime. Okay, So this is how we work our way up the ladder. We solve this 1 degree of freedom problem. We need to work our way back up and reconstruct the motion. That's a general feature of the theory of reduction. You use symmetries to reduce the complexity of the problem, but then you must reconstruct the motion. Okay, and we're in good shape here. You see we have solved, and let's bring in some nice colorful, do we have some nice colorful, it's gone missing. Oh, here it is, the red. Okay, so you see we solved, we got the T of R. That's not controversial. We have a nice formula there for T of R. It's in, you're going to invert it to get R of T. We'll talk about the difficulty level later today. Okay. And now we have the phi of T. Again, it's given to us as an integral. We must integrate. Okay, so thinking back to those slides, earlier in today's lecture, we looked at a newsletter way back from 1977 when newsletters were printed on paper. I remember those days. It's kind of nice actually having them printed on, frankly, I like it when they're printed on paper. But, okay, you remember the Earth's orbit, there was a diagram with the Earth's orbit, the Martian orbit, and the trajectories of these spacecraft, and they were labeled with the time. So the functions we have here, R of T and phi of T, if you know those functions, then you could produce such a diagram, right? Because we would start here with a two-dimensional diagram, and you could repeatedly plot points, right? Here's the angle phi, here's R, the distance. So with these formulas for any value of the time t, you could plot a point and voila, you could produce such a diagram. So the point is, these formulas are complicated. They are not presented in chapter 8 of Taylor because they're a little too complicated. What we're going to do, and again, functional relationships, we're going to solve for R of phi, okay? Remarkably, this is a simple formula. Okay, this relationship between R and phi, and again, that's the shape of the trajectory. The shape is a simple formula. It is in the chapter 8 summary. These formulas, again, in general, they're too hard to solve. You have this effective potential. For problems involving gravity, of course, the effective potential has two terms. You've got the Newtonian gravitational potential, and you've got the centrifugal barrier. Okay, but there are some interesting things here. We're going to speak in generality here. Let's compare things like the Kepler problem. Again, the term Kepler problem is that's the term that is used when you have a gravitational problem. We're going to compare that with a different problem. Suppose you have a spring, a Hooke's law spring, and this particle mu is getting pulled back to the origin by a Hooke's law spring, a perfect spring with zero rest length. That is to say, if the two original particles, remember the story began with a 6 degree of freedom problem, if these two original particles are connected by a massless spring, and there's no gravitational interaction, just that spring, we can certainly solve that too, because again, that's a central force. Okay, so here's the remarkable thing. In both cases, in the case of the gravitational problem, as well as the case with the spring problem, you get elliptical orbits. The funny thing is, for the gravitational problem, it's one of the two foci. The force center is at one of the two foci. So for example, planets orbiting the sun is at one of the two foci. The sun is at a focus, okay? For the simple harmonic oscillator, you have elliptical orbits, but the force center is at the center of the ellipse, not at one of the foci. So let's talk about this. And there's an interesting statement here about frequencies. Okay, so remember for the bound orbits, this is where we have the elliptical orbits. Turns out the same framework can also talk about the hyperbolic trajectories. You remember from the physics 7 sequence, the hyperbolic path. That's what we need to analyze the swing by. When a spacecraft swings by Venus and profits from that interaction, we can analyze that, again, using the same technology, so to speak, the same mathematical framework. But first, let's talk about these bound orbits, right? Elliptical. Okay, so the radial motion, this function r of t is periodic. Okay, remember the two classical turning points. There's a minimum value, which we had here, the r min, and there's a maximal value. R of t just simply goes back and forth between r min and r max, and we know how to compute the period, right? It's essentially the same integral. In our book, we have to use a tau. The reason is capital T is reserved for kinetic energy. Think of all those fun Lagrangians we looked at. Capital T is the kinetic energy. We use tau for the period. Okay, and so one full cycle involves two traversals. So we've got 2 times the integral from r min to r max. Okay, and it's the same integrand. Now we can use r. There's no need for a prime here. Remember earlier, we had to put a prime on the variable of integration because we had used the symbol r for one of the limits. Okay, we're not plagued by that annoyance here because the limits are r min and r max. So the variable of integration, we can use r, and there will be no confusion. This structure is the same. We got the 2 over root mu. Inside the root, we got the 2 over mu is what I was trying to say. We got the E minus the effective potential evaluated at R. Okay, so we have this formula for the period. Very nice integral. Something truly remarkable happens both for the Kepler problem and for the two-dimensional harmonic oscillator. Okay, these are special problems. Again, the Kepler problem is the problem of Newtonian gravity. So that's, think of planets and comets, etc., orbiting the sun. Okay, so something remarkable happens. You can ask the question, what is the change in phi? This is a major question. Change in phi for one cycle of the radial motion. So for one cycle, okay, remember for these bound problems, the radial motion is periodic of radial motion. Okay, let's underline that because this is important to us. And something remarkable happens here, both for the Kepler problem and for the two-dimensional harmonic oscillator, you get closed orbits. That is remarkable. Let's squeeze it in here. We can certainly squeeze it in here. For the Kepler problem, okay, for the Kepler problem, you have a nice elliptical orbit. And following the Chapter 8 summary, we have some foundation results, really important central results. In the Chapter 8 summary, we like to put the axes like this, and the perihelion here is on the positive x-axis. Okay, so for the Kepler problem, it looks like this. For the two-dimensional simple harmonic oscillator, so I'll write 2D simple harmonic oscillator. The ellipse is centered at the origin. Isn't that funny? They're both elliptical, but for the two-dimensional harmonic oscillator, the ellipse is centered at the origin, like so. Okay, and the general case looks like this. The point here, in general, orbits do not close. These are both very special state of affairs. Here's the general case. It looks like this. You have oscillatory motion for the radial problem, right? And so in general, it kind of goes like this. Yep, I'm drawing. In general, the orbits do not close. Let's see if I can write that here. Orbits do not close. Okay, and let's way down the paper like so. So this is a remarkable comparison here. And let's appreciate what's going on. Here, we have a very special relationship between frequencies, the crucial concept here, frequencies. Remember the radial problem, this was our 1 degree of freedom problem. We had a particle of mass mu traveling along this one-dimensional R axis, moving back and forth. If it's a bound problem, then that particle of mass mu is moving back and forth between two classical turning points. There's a certain frequency, right? It's periodic motion, so the reciprocal of the period is the frequency. We can speak of the radial frequency, and then when we start this reconstruction process, we're working our way back up the ladder. We want to know about the 2 degree of freedom problem. The question is, what is the frequency for phi, right? Because now we're going around and around in this picture. And the remarkable thing here are the degeneracies. So for the Kepler problem, this is the fun part. Let's go through one cycle of the radial motion. So here we're at the minimum radius, then we go to the maximum radius, and then we go back to the minimum radius. So for the Kepler problem, the two frequencies are identical. One cycle of the radial motion is precisely the same as one cycle in this 2 degree of freedom picture, okay? Let's compare that with a simple harmonic oscillator. So here we have the maximum R, then we go to the minimum R, then we go to the maximum R, then we go to the minimum R, and then we go back to the maximum R. So we go through 2 cycles of the radial motion. Going around this picture one time, so in the 2-dimensional space, we have periodic motion. Going around for one period in this 2-dimensional diagram, we actually go through 2 cycles of the radial motion. So that it's interesting that there's a factor of 2 relationship between the frequencies. In general, the orbits do not close. That means you do not have periodic motion in this 2-dimensional picture. You get a big mess. And you see I did a good job of drawing a mess. That's what you get. The orbits do not close. You can wait as long as you like. The orbit's not going to close. That's the general state of affairs. It's only for very special, and these are both very special cases, the Kepler problem and the 2-dimensional harmonic oscillator, that you have these degeneracies, right? Here, the 2 frequencies are equal. The radial frequency is equal to the frequency in this 2-dimensional picture. And here there's an interesting factor of 2. The radial frequency is twice the frequency that you have in this picture. Okay. Then when you get to quantum mechanics, there will be some remarks. The reason for these degeneracies there are extraordinary symmetries in these problems. And later in the course, we'll talk some more about these symmetries. And then I mentioned when you get to the quantum mechanics, you have degeneracies, right? The energy levels for non-relativistic hydrogen, you have this amazing degeneracy. The energy levels depend only on the radial quantum number. So later in today's lecture, we're going to talk about some remarkable things about the Kepler problem. The fact that the period, right? You know that the square of the period is proportional to the cube of the semi-major axis. That's the result from the 7 sequence, Kepler's 3rd law. And there's another result that the total mechanical energy, right? Kinetic plus potential, that's a conserved quantity along an orbit. It only depends on the semi-major axis. It does not depend on the semi-minor axis. So those are 2 interesting results. The period depends only on the semi-major axis. And let's see, what was the other one? Wait a second, the total energy, right? The total mechanical energy, yeah. Okay, so let's talk about how we're going to prove these fundamental results, and we're very interested in this one here. Let's not delay in putting some red color here. Okay, this is an important milestone, finding the functional relationship, and again, it's a simple formula, the functional relationship between R and phi. This formula enables you to draw the elliptical orbit. You can draw the closed curve, for example. If it's a hyperbolic trajectory, you can draw that using this formula. And again, the other ones are much more difficult, so we want to investigate those formulas. Okay. So we're going to transform the differential equation. Okay, so what does that mean? Well, we have a differential equation, right? We had the mass times the acceleration, and we had the minus sign and then the derivative of the effective potential. That's a difficult equation to solve. Now we're going to do a transformation, and rather than solve for r as a function of phi, we're going to define this lowercase u simply as the reciprocal of r. So there are a couple of things to be said. So first of all, let's emphasize this is a lowercase. Okay. And this is simply the definition of this lowercase. Okay. So over hundreds of years of solving this problem, people realized this is a useful thing to do, to find lowercase u to be the reciprocal of r. Okay. And we had a differential equation for, remember the original differential equation here, this was a differential equation for r as a function of t, right? So of course this was a second order differential equation. We had the acceleration times the reduced mass equaling the minus the gradient of the potential. That's a differential equation. And again, the functional relationships, we were interested in r as a function of t. So we had that differential equation. Now what we're going to do, we transform the dependent variable. So this portion here, we're going to transform the dependent variable and we're also going to change the independent variable. So also, okay, so our goal now, our goal in life is to study u, that's the lowercase u, as a function of phi. Perhaps the motivation for choosing the letter u is that in Newtonian gravity, capital U, right, the potential energy is a negative constant times the reciprocal of r. Perhaps that's a motivation, doesn't matter. This is simply a definition here. Lowercase u is defined to be the reciprocal of r. Okay, so we're going to transform the differential equation. Again, functional relationships. R of t, our original second order differential equation was for r of t. That's the radial variable as a function of the time t. Differential equation. So we had derivatives of this object. They were time derivatives. We're going to transform, and so we'll get a differential equation that makes a statement about this function u as a function of phi, and derivatives of this function u as a function of phi. So how would you do that? Well, first of all, let's observe, okay, if this is the new function, we're going to be studying okay, and how can we compute the derivatives? Remember, this is a function now of a single variable. So what can we say about the derivatives? Well, here's what we do. Consider u, and we'll do functional composition. Okay, if u is a function of phi, then we can insert the function phi of t. This is functional composition. The resulting object is a function of time, and we can compute the derivative. The appropriate notation is the ordinary derivative, right? This construction is a function of the time. It's a function of a single variable, and so we can compute this derivative. Of course, we do this using the chain rule. And this is the quintessential example of the chain rule. The short answer is this is u prime phi dot, right? That's the short answer. It's very compact notation. Perhaps it's confusing. So let's write this in more detail. What does this mean? Well, we have the derivative of u with respect to its argument, that's du d phi. And then the chain rule says multiply by d phi dt. And as always, a sanity check on your chain rule is if you simply cancel off these d phi's as if this were division, which it is not. But you can cancel off these d phi's, and what remains is du dt. That's what we have here, du dt. Okay, now d phi dt, of course we like this, right? Because we have a conserved quantity, right? D phi dt is the cursive lowercase l over mu r squared. Okay, so this calculation here shows how you transform the first derivative. Then the same technology is used again a second time to transform the second derivative. We'll skip that here in lecture, it just gets rather tedious. Let's just cut right to the exciting result. And here's the exciting result. Okay, now that is a cool equation. You see, we're going to be able to solve this. Once again, we're using our knowledge of chapter 5. Now let's take this opportunity to remind ourselves, the midterm on Friday, the emphasis will be on problems from chapter 7. And you can see that structure in the sample midterms. There are 2 sample midterms, sample A and sample B. However, those problems require you to look back and use your knowledge from chapter 5. We're going to use our knowledge from chapter 5 to solve this equation in the box. All right. Notice if the constant, this is a constant here, gamma is a constant we defined last time, capital G times M, capital M, little m, mu, et cetera, and so forth. These are a bunch of constants. So if this were absent, you would have a very simple equation like we had for the simple harmonic oscillator. It's even simpler because that's a -1. For the simple harmonic oscillator, you have a minus omega squared. Here's just -1. Okay, so how do you solve this equation? Okay, the simplest way to do it, if you want to invoke your knowledge of chapter 5, define a new function which is equal to the function that we want plus a constant. Okay, so you're simply shifting by a constant, so you can absorb this constant into the new function w, and then the equation for w truly is a simple harmonic oscillator kind of equation. Okay, so the upshot is that this u, which is the reciprocal of r, is gamma mu over L squared. If you hear a cat scratching at the door, just ignore it. Sometimes you just have to ignore them. The cat, if we let the cat in here, it's just going to be a pain. All right, so cat stays out. Okay, so this is precisely the structure that we expect, right? Notice that if you plug this into here, there's a minus sign, so the constant cancels away, and the cosine of phi, this is what we expect, because again, this is purely a -1. In chapter 5, we would have basically a minus omega squared here, and you would have an omega here. But here we have that simplification. This is just a -1. And remember, u is the reciprocal of r. So this is the celebrated result. This is the result that is in the chapter summary. This amplitude is a constant. Okay. So the amazing result, the way you see it in the chapter summary is the following. R equals C over 1 plus epsilon cosine phi. So this is the formula for an ellipse or a hyperbola or a parabola. This is the formula, the way you see it in the chapter 8 summary. Okay. You can see it's just a reorganization of this formula we just derived. This constant here, we favor this epsilon. We prefer the epsilon. And this is the, some people pronounce it eccentricity, some people pronounce it eccentricity. Okay, so if epsilon equals 0, you have a circular orbit, right? If epsilon equals 0, then this term here in the denominator vanishes. You have a circular orbit and the radius is c, okay? Then if epsilon is between 0 and 1, you get the hyperbolic orbit. Now notice the structure. Well, let's draw a picture. And of course, in Taylor, we have the angle phi relative to the positive x-axis. Okay. And it looks like this. For an elliptical orbit, think of a number like 0.5 for epsilon. So when phi is 0, the denominator, this cosine is a +1. The denominator is as large as it's going to get. So r is as small as it's going to get. That's when phi is 0. And then over here, we have the opposite. R is as large. Okay. So this will be our typical picture of an elliptical orbit using this formula. Okay, and this is the way it is in Taylor. We could have included an offset. So we could have rotated this ellipse. But the way it's typeset in Taylor is without, right, you could put phi plus some phi naught here, and that would rotate the ellipse about the center of the picture. But this is the way it is in the Chapter 8 summary. So this will be our most common form for the formula. Okay. So there are several things to be said here. Notice what happens if you multiply this denominator over to the left. 1 times r is just r. And then we have an epsilon. And r cosine phi is just x. So r plus epsilon x equals c. So again, this is a funny formula, but this is an equation that gives you an ellipse. Okay. So again, this is an ellipse in the plane polar coordinates, right? R and phi. What we want to do is make a connection with the familiar, right? People have been studying ellipses for at least 2,000 years. And typically, when we first start talking about conic sections, we talk about quadratic polynomials. So let's take a moment to reunite this, right? And of course, we have a host of fond memories of super eggs, right? Earlier this summer session, we were doing a lot of calculations with super eggs. And the formulas for a super ellipse, right? Very similar in structure to what I just mentioned for an ellipse. For a standard ellipse, most people will tell you, well, it's a homogeneous second order quadratic polynomial. You plot it, you get an ellipse. That's an ellipse that's centered at the origin. Okay. What we want to do is take some time to talk about this formula here and how this relates to the more conventional formulas for ellipses. Most people, if you ask them about ellipses, they will start telling you about quadratic polynomials. Okay. So again, this is an alternative form here. Okay. So what you can do from this form, you square it. Okay, there's quite some algebra. I think we're going to skip through a lot of the algebra. Let's make a comparison with this diagram. We're going to draw the ellipse like this. Okay, and when it speaks of the semi-major axis, right, this is the semi-major axis. I'll use a different color here. Okay, so the lowercase a is the semi-major axis, and the lowercase b is the semi-minor axis. Again, the remarkable results in terms of physics, what's going to be remarkable is that the total mechanical energy depends only on the lowercase a. It is independent of b. And furthermore, we have Kepler's third law. We're going to show that the period, at the time it takes to go around once, the square of the period is proportional to the cube of A. And again, independent of B. We'll see that B depends on the angular momentum. So again, these statements are that the total mechanical energy is independent of B and the period is independent of B. Okay, so we have these nice relationships. The two foci, let's diagram it like this. Here's one focus. Here's another focus. And again, we have these two foci. And this distance here, from the center of the diagram, from the origin over to this focus on the right, that distance is epsilon, the eccentricity, times A. Okay, so it's all coming together. This parameter C, you can read it off from the picture. Because what happens when phi, in the language of degrees, when phi is 90 degrees, we'll talk about that. In the language of radians, of course, that's pi over 2 radians. So this distance here is C. Okay, and again, I'm drawing that in a different color. Okay, and so again, you can see that, again, following the orbit, when you have 90 degrees there, the cosine is 0. And your distance from the origin is just C. Okay, so there are some algebraic identities. Again, there's a nice summary in the text, so I won't write them all here. But these quantities then can be related to the physical quantities. We had the gamma, right, we had our gamma, mu, and L squared. Okay, so let's talk about a couple of surprising results. We want to discuss the total mechanical energy, and what we're going to see is that the total mechanical energy for an elliptical orbit we have this relationship that the total mechanical energy is minus gamma over 2A. Okay, and then we're going to discuss Kepler's third law. Okay, the relationship between, or typically you talk about the square of the period and the cube of the semi-major axis. Okay, now for Kepler's third law, there are two forms. There is an exact form and there's an approximate form. Remarkably, the approximate form is more popular. Why is the approximate form more popular? Because for the approximate form, you have this universality. All the planets in the solar system, if you make this approximation, then for all the planets in the solar system, again, the square of the period is proportional to the cube of the semi-major axis. Okay, we'll talk about this approximation. Strictly speaking, there's a distinction to be made, and it has to do with the distinction between the center of mass of the solar system. Suppose you have the sun and the planet, right? The center of mass of this two-particle system may well be inside the sun. So there's a certain distinction between the distance between the two particles and the distance between, say, the planet and the center of mass. They're very similar. Okay, so what we'll do is go through that calculation and appreciate the distinction. Okay. Okay, it's very useful to write down the energy, right? So let's look at R min. Remember, this is one of the two classical turning points. If you look at the 1 degree of freedom problem, the particle is moving along the r-axis back and forth between R min and R max. And the good news is, at either of those turning points, in the 1 degree of freedom problem, the particle is momentarily at rest. Okay, in the 2 degree of freedom problem, it's still going around the force center. But looking at the 1 degree of freedom problem, it's momentarily at rest. So for example, at R min, okay? The same would be true for R max, all right? But it's useful just to select one of them. This is saying the kinetic energy, and remember our notation T, that's a capital T, that's the kinetic energy. At the turning point, the kinetic energy is 0. Here, this is for the 1 degree of freedom problem. Okay, so you can write this out because you know from our formula, what's the minimum value? What is R min? Well, what's the smallest R can get? The question is the same as what's the largest this denominator can be? The largest this denominator can be is 1 plus epsilon because cosine maxes out at 1. So if you have C over 1 plus epsilon, okay, that gives you the minimum radius. Okay, so you plug that in. We know that this is our R min. You plug it in here. And then again, there's some algebra. One of the results that is presented in the chapter summary follows from this, that the total mechanical energy is minus mu gamma over 2L squared. And there's a 1 minus epsilon squared. Okay, so that formula is in the chapter summary. Remarkably, and you should go through this as a nice exercise, this simple formula is not in the chapter summary. Somehow, in my opinion, that's an omission. It's important to observe that the total mechanical energy is minus gamma over 2A. And this is well known for circular orbits. Obviously, a very important sanity check is for circular orbits. Okay, so let's talk about Kepler's third law. And we want to appreciate that there's an exact form and an approximate form. And as I mentioned, the approximate form is wildly popular. Everybody loves the approximate form. Okay, so for Kepler's third law, the starting point is the conservation of angular momentum. And this phrase that you hear all the time, equal areas in equal times, right? That's part of the lore of the Kepler problem. That's really just the constancy of the angular momentum. So let's write that out. We have L, the cursive lowercase l, equaling mu r squared phi dot. And this is a constant. Let's appreciate that this is telling us that the rate at which we sweep out area, let's draw the picture. So here's the origin. There's the orbit. Okay, now if you draw a straight line from the origin to the point, as time goes on, the particle goes around and that straight line sweeps out area. The rate at which it sweeps out area, that's what is of interest to us. So here's a typical time, and a short time later, we're here. So how much area is in there? Well, it's a calculation where we must compute the area of a triangle, right? We can approximate this as a triangle and compute the area. So the rate, we sweep area at a rate right, there's a factor of a half here because we're talking about triangles. You know, triangle 1/2 base times height. So we got the 1/2, we've got r squared phi dot. Okay, let's appreciate this is exactly what you get from the standard notion of the area of a triangle. So this is at time t. And later at time t plus dt, we're here. Okay. So what's the area? Well, it's 1/2. Then you have a factor of r from this edge, and then r, the product of r and phi dot times dt, that's the other edge. So this is the rate at which we sweep area. Okay. So with that in mind, let's continue sweeping area for a full period. Okay, so write this for a full period. Okay, And the good news is we're going to sweep out the entire ellipse. Okay, what's good about this news, the formula for the area of an ellipse is very simple. The perimeter is terrible. Okay, for a circular, if you have a circular orbit, we have a simple formula for the area and a simple formula for the perimeter. But for an ellipse, okay, so here's our ellipse. Okay, remember, there's A, there's B. The area is just pi AB. Okay, so we have a simple formula for the area of the ellipse. And you can see you can get that from just doing a linear transformation on the plane. Just stretch out, draw a circle, then stretch left and right, and you get this picture. So you can prove this formula quite easily. The perimeter is an absolute disaster. You have to invoke these special functions from mathematics. So the good news is we don't need the perimeter. We just need the area. We have a statement here that the rate, this is the rate at which we sweep out area, okay? And you see, we get it from these fundamental constants. So we have a very clear statement about the rate at which we sweep out area, and we know the total area of the ellipse. And the upshot is Kepler's third law. Now let's talk about the two formulas. Okay, we have equation 8.54, and this is exact. Let's understand why this is exact. And then the next equation, which is the more popular one, equation 8.55, again, it's more popular, but it's an approximation. Okay, let's understand this. All right, so it's this calculation here again with the area. We can compute this exactly. And what we get here, tau squared. We got the small font here in the notes, and we got a 4 pi squared mu. Over gamma, remember our constant gamma, times a cubed. So that's exact. You can rewrite this as a 4 pi squared over gm. And remember, this is the crucial thing. Here's the transition. Capital M, I must emphasize, this is one of our foundation things, M1 plus M2. Okay, and there's an a cubed here. All right, so that's the exact formula. Why would you do the approximation? Well, the approximation, you copy this over, and so let's copy this here and say M, which is exactly equal to the mass of the sun plus the mass of the planet. Right, that's exactly true. We're going to approximately say M is approximately the mass of the sun. To many digits, that's a good approximation. So if you do that, you just write the same formula, and then you get the following, that tau squared, you see why this is a popular result. Tau squared, the period squared, is 4 pi squared over g times the mass of the sun times a cubed. Okay, so this is the universality for all planets in the solar system. You have this wonderful relationship. The square of the period is proportional to the cube of the semi-major axis. The constant of proportionality is the same for all the planets. The truth is it's slightly different, right? The truth is it's really mass of sun plus mass of planet. But for something like the, typical run the numbers, you're making an error out there at the 6th digit. It's a tiny part per million error, so it's quite acceptable. Okay, so that brings us to the end of the hour. I'm going to click the button to stop the recording, but I will stay here. Stop recording.